Did I have that in the... No, I didn't. Good. What's going on, party people? Hold on. Let's set the tags. I think I should also set a description, maybe. Maybe setting a description will help. I don't know. Maybe at this point I'm just coping. Maybe I'll never get views, but... Yeah. Let's set a description. Editing videos, studying real analysis, and maybe taking a 10-minute power nap between. Who knows? Add a tag. Grind set, study, motivation, school, math, real analysis, hard, not easy, inspirational, sigma. Save. Okay, guys, what are we doing? First things first, I recorded a episode. Well, not just me, but me and the boys recorded an episode of the One Day podcast that I should probably edit and upload today. Might as well. After that, what else is on the agenda? So recording that, editing that video, finishing up our real analysis studying, and hopefully also finishing up homework that we have due for that class. And then by tomorrow, so we're still on track, I think. Today we were to start reviewing past homework, so we're a little bit behind actually, but for good reason. Had to get some groceries today, okay? So that took some time out of the morning. But aside from that, yeah, we can read our the chapters in the book, and yeah. What else? I'm blanking. Yeah, read chapters in the book, and then let me write down week 12 things. So week 12. So what are my goals for this week? Well, I'm gonna grind, studying finals, no fast food, stop using social media, record and edit one YouTube vid, gym consistently, experiment with one song. Okay, that's our goals for this week, but we've got some editing to do, right? Can we get much higher? But first, before we get into all that nonsense, let's talk it out a little bit, okay? What's going on? What's happening? Let's write down our goals for today. April 28th, 2024. Edit one day pod. Read. Finish 104 textbook. Finish 104 homework. And then tomorrow we'll start. I just realized I have review sessions I should probably note. April 30th, 2 p.m. 2 p.m. Math 104 review session. On Zoom. Okay, I guess the link is just somewhere. Zoom. Save. What else? Is there a review session for Solid State? I don't think so. There is a review session. Yeah, on May 2nd, Thursday. Usual time as a class, which is 11 to 12:30. So, review session. Is there a review session for quantum mechanics? I highly doubt it. Yes, there is no review session. Okay. So, then tomorrow we start basically grinding past midterms and past homeworks. So I think the first thing that would be the most helpful is to grind on previous past homework. I mean, midterm problems, just because they'll be similar. So let's change tomorrow's goal for review past midterms with emphasis on 137B and 104. I might just emphasize quantum mechanics that day, because I didn't really do well on the first quantum mechanics midterm, but I did better on the second one. But I don't know why I did better on the second one. I just kind of somehow ended up doing better. So we should probably spend our time trying to iron out the classes that we're the most confused in. I'd say 104, real analysis, it's confusing, but it's not hopelessly confusing. It's not like I'm like, I have no fucking clue what's going on. Solid state, it's also not hopelessly confusing. I think solid state, actually, I have a good chance of doing a little bit well if I just practice doing the problems. And like energy density, there's like stupid things that they always ask for. That's like it's kind of hard to remember like the steps of like how to do it, but it's fairly straightforward once you know the steps, how to just integrate it into the problem, which sounds super straightforward and sounds like this is like, of course it's going to be the case. That's like the case for everything, but you know, listen, shut up, bro. Okay. I think I have too much noise on this. I'm going to put this to the side. This is like a to-do list for the week, or like not necessarily for the week, but for just other stuff. I'm going to put it to the side because I think it's distracting me. It's too much visual noise and it's causing me to not look at my daily goals. So we'll put that there. Weekly goals are on the back of this. On the front of it are timestamps though. We got to edit this video right quick. So we'll edit the video, finish reading the textbook, and then finish doing the homework. That'll probably be off stream because I might take a break after finishing reading the textbook. So let's do it. Let's change the to-do list. It's going to be read chapters 6 to 7, real analysis. Let's finish, edit, 1 day pod, finish 104 homework. Okay, there we go. We got our to-do list. And now all that's left to do is to open up Adobe Premiere Pro and let's get to editing, guys. Before that, let's go fill up on water in the Brita filter because I'm running low on water. Whoa, can we get much higher? Guys, Premiere Pro is not oh. Is it gonna close? Yeah, it closed because I pressed force quit. Don't reopen. All right, you can see all of my projects here. Let's make a new project. I didn't make a new folder yet, actually, so let's do that first. Videos, Premiere Pro, 1A, week 12, footage and outbox. Let's get our footage going. I might actually just mute. How would I do that? I don't think I can do that. I was gonna say I might mute. I don't know how to do that. I don't think I can do that. Mute Premiere Pro specifically, but allow you to hear like music in the background. I don't think I can do that. Actually, I probably could. Audio input capture. No, I can't do that. Remove. Yes. I could do a browser, I guess. Minecraft chill music. Can I do this? Is this legal? I mean, you guys can obviously hear it coming from this. No, I don't know if I can do this. I was about to say I can do I can throw on an episode of SpongeBob. But no, I'm not gonna do that. Yeah, okay, you guys will just kind of hear it, I guess. Let me grab the footage though.
Paul, this is how it happened.
Yes, here it is. All right, I think I'm gonna not let you guys listen to this. You guys can just look at the process of me editing it, but you can still hear me talk. So, wah, cry about it. I do not care. You guys want to see how I make the, oh, what the fuck? I just copied the JPEG. You guys want to see how I make the thumbnail every week? Look at this. I use a very special image editing software. Okay. I use Keynote, Apple Keynote. And what I do, I just have a text box here. And then I just, boom, change it like that. File, export to images, save, put it in here, export, boom. And that is how I make the thumbnails every week. Just makes it so that it's all the same all the time, no matter what. So let's open this up, create, and boom. This is a little key tip. Hey, if you guys want to know how to edit, I mean, I'm not a pro at editing by all means. So this is not like a masterclass in how to edit, but yeah, you can't hear anything. Nice. We can start it from here. What? Why did notes just quit? Yeah, you can kind of see what do I do? So what I do on the side, ignore. What I do on the side is that for timestamps, I'll kind of do something like this. And then I'll just put in the timestamps. But the timestamp is not going to be the same in the timeline as when I'm finished it. So you can just add a marker in Adobe Premiere with just pressing M, right? Yeah. If you press M, you can add a marker. And then it helps because then you can just put the marker at each like kind of timestamp, because I have timestamps written down for like the raw file. So I'm not going to like go and move this all the way to 0 seconds in because I'm just going to skip to these times that I kind of wrote down. We'll zoom in a little bit more too. And then I'll like, for this, because I only know the timestamp of the start, so then relative to that, I'll just kind of press space, and then I'll write down, okay, what's the title for this? So this is going to be like, this is kind of like the title of like what'll appear in the chapter thing. So. This is just kind of boring because I'm just editing this and you can't hear anything. It doesn't matter though. Who cares? Okay, so this is when Mike's weeks start. Yeah, basically right now I'm just going through timestamps that I've written down, putting a marker there, and then just writing down the title of what the timestamp is going to be. And I'm just kind of combing through and doing that. It's a little bit more work, but it helps with the actual watching of everything. Is this entertaining, guys? Um, don't worry, guys. We're almost done. I swear to goodness. We can almost move on to the actual interactive part of this, where I don't have to mute. I now realize what he wanted to cut up. Okay. That's it. All right. Now we can go back to you guys hearing everything. So now, once I've done this, what I'll do is I will go to 0 seconds. You go to sequence. You press close gap. Boom. Puts everything together. And then you can just sandwich it to the start. And then, now, what I'm going to do...
We get into that. How your week was?
My week was podium. It was alright.
Bro,
We get into that. How your week was though overall? If you could.
so I like to do a little bit of a slow fade in, 50%, and then we have like some title cards, you know. So let's say hello ladies and germs, welcome to another day of the, and then middle align, Helvetica, bold. Let's do font size 60. Let's do 50. Don't need it that loud. Stroke, yes. Put it like that. What happened? Okay, there we go. Space it out a little bit so that we can align it. And then put this and say 1 day podcast. Boom. 100. What the hell? This one. 100. Middle align, please. Can you middle align? There we go. And look at that.
We get into that. How
Kind of doesn't look super. There we
your
go.
week was though overall? If you could.
And then what? Let's do it up until 5 seconds. And then for this, you can just do a simple cross dissolve.
We get into that.
To
How
let
your
it
week
fade
was
in.
though overall?
So let it fade in a little bit slower.
We get into that. How your week was though overall? If you could.
And then boom. And then just talk today. What did we do? What did we do for this one? We're straight to business. It's finals week for Paul. Mike is starting a new job. Jesh's laptop is still broken. Middle align, boom.
In terms of goals,
Bro,
in terms of this life,
he
bro.
asked the same thing last week. And you asked the same thing.
for real?
Yes, we both. Enjoy a beautiful watching experience, especially thanks to the timeline in the play bar. Three faces. Boom. So just some text.
For real?
Yes, we both asked the same thing.
So anyone want to answer?
Yeah, I like this. So we can throw a cross dissolve at the end. Let it slowly fade out. And then at the same time, we will increase the opacity of this to come back to 100. Boom. And then look at this.
So anyone want to answer?
My week was good. It was chill.
Oh, for me,
Okay. And then also, you might notice there's some Discord stuff up here. Now, I don't quite know how to exactly crop this out. So what I do is I just take some text. I make it pretty big. Let's say 300. That did not actually change the size of the text. Make it 300. Take away the fill. Put a background. Make it black. Make it 100% so it's not opaque at all. Put it as the topmost layer. Adjust it a little bit so it's like that.
Yeah.
It's
Yeah,
good.
but
And
in
then
terms
boom,
of goals,
covers it up. And now, look at that. It looks like a full thing. And now we can extend it all the way to the end. That's going to be annoying as hell.
we got Danny our conversation.
And the video just ends there. That's totally fine. Let's rename the sequence. Just for the sake of organization. 1 day, week 12. Then we can save this. Oh, why is our project named Untitled? Can I rename the project? I guess I can't rename. Oh, it's because when I was making it, I didn't name it. I did name it, did I not? Maybe I didn't. Whatever. We will change the name of it later. But so now what you can do is you can do Command Shift M. Or what is it? How do you go to the next marker? Shift M. Okay. So Shift M, go to the next marker, and then you'll see the little timeline here. And now what we can do is we can just 0031, boom, fill in all the timelines. So Shift M, 216, so 0216, go to the next one, Shift M, 618, 0618. I could probably make something to automate this, but 725, 0725, Shift M, 808, whoa, and heartbreaks, 0808, Shift M, 1541, 1541, Shift M, 1745, Shift M, 1941. That's when World War I happened, right? World War II? What was important in 1941? Pearl Harbor. Operation Barbarossa? Okay. Sure. Song 2631. Also gonna edit this. So let's insert the song into the footage folder, videos, Premiere Pro. So even if it's very short, I like to just keep all of my footage that I'm using for the project in one thing, so I can just insert it. And if I'm opening the project later, it'll still be in that folder, like it won't be anywhere different. Just that it's easy to always go back and open up a file, but I did that, okay? Y'all recommended jazz, so I made a jazzy beat. So you need to make this a lot lower in volume. I did that, okay? Y'all recommended jazz, so I made a jazzy beat. So it's linked in the Discord. Honestly, I like doing those, like making these like bonus song things. It's actually pretty fun. It's with music in a different genre. Let's insert some text. Now we have to fix our mistakes that we made previously. Can you fill, please? Okay, there we go. And let's make it 50. Center line, there we go. Go to the effects, cross dissolve. Put it down here, please. I did that, okay? Y'all recommended jazz with music in a different genre. I did that, okay? I did that, okay? Y'all recommended jazz, so I made a jazzy beat. So it's linked in the Discord genre. I did that. Slowly decrease the levels, okay. I guess. Y'all recommended jazz. So I made a jazzy beat, different genre. I did that, okay? Y'all recommended jazz, so I made a jazzy beat. So it's linked in the Discord. Honestly, I like doing those, like making these like bonus song things. It's actually pretty fun. It's making me like have bonus song things. It's actually cross dissolve where it fades away. Let's do it like that. It's actually pretty fun. It's making me like, it's actually pretty fun. It's actually pretty fun. It's making me like have more fun with music because now I've like decrease it. It's actually pretty fun. It's making me like have more fun with and then increase this. It's actually pretty fun. It's making me like have more fun with music because now I've like back to normal. It's actually pretty fun. It's making me like have more fun with music because now I've like different genre. I feel like I should also decrease the opacity of. I did that. Okay, y'all recommended jazz. It's just to like 80, slightly darker, 70 maybe. So I made a jazzy beat. So it's linked in. It's actually pretty fun. It's making me like have more fun with music because now I've Back to 100. Boom. Bonus song thing. I did that. Okay. Y'all recommended jazz, so I made a jazzy beat. So it's in the it's linked in the Discord. Honestly, I like doing those, like making these like bonus song things. It's actually pretty fun. It's making me like have more fun with music because now if I before when I used to like okay, there we go. Go to the next marker. 29:48. Next marker 34:36. This is 41:19. 41:54. This one is 47:10. 51:34. 53:06. 56:56. This one 59:46. 1:07:22. Okay, so that's all that. We need a description. What's our description? What's it gonna be? Let's see. What did I write at the start? Today, straight to business. Finals week for Paul. New job for Mike. No laptop for Jesh. Performance as well. We need to include that. So let's open up Lay Doc, Lay Epic Doc. You can see. I'll put it on here. You guys can see our performance. Performance and screen time. Okay. Boom. All right. And I think that's it. Performance and screen time. We got timestamps as well. I think I should put the performance above the timestamps. Because the timestamps, I mean, people can click on it in the description, but it also just appears on the scroll bar. So like I just click on the scroll bar first. So one day, week 12, that's what it is. We're gonna export it. I don't actually know if my computer can handle streaming and exporting at the same time. That would be interesting to see. Pretty sure it could though, pretty sure. But we'll see. I definitely can't. Usually I'll do compression. So I'll upload the video uncompressed and then to store it on my computer, I'll compress it. Just to make storing it better. But yeah. Okay. Now, I know what you guys want. You guys want some background music. I'll give it to you guys. Here you go. Minecraft music. Now, edit the to-do list. Now we're cooking with gas. Okay. So this is actually going to take 8 minutes. So you know what I'm going to do, guys? While this is going on, you guys can watch this export. I'm going to take a 10-minute power nap. Set a timer for 12 minutes.
12 minutes.
And this time it's for real. It's a for real power nap. Because I set the timer for 12 minutes. But yeah. So you guys can watch this in code in real time. I'm going to go take a quick power nap. And then we will be grinding on studying. Hope you didn't miss me too much, guys. Turn the music down a little bit. Okay, so that is that. Actually, what I want to do is I want to rename that Adobe project. Not have it called Untitled. I don't like having a bunch of untitled projects. So one day, week 12. Okay. Now we will upload it. Let's open up this. I think I should probably have this off screen, because I have no idea what can pop up. Manage videos. Let's take the tags. From this video. Create, upload video, select files. It's 4.51 gigabytes. We're gonna have to definitely fix that. What's the title gonna be? What's the title of the video gonna be? Title is just total clickbait. Things are getting serious. I don't even know what that means. No, it's not made for kids. God damn it. I copied the tags. Oh, just to delete them. Just to replace it with something else. Hold on. Okay, there we go. Next, add an end screen from the last one. Save, checks, visibility, set it as public, publish. Boom, guys, boom. We've got our video uploaded. Oh shit, wait, it's still uploading? Can't close it out yet. Oh, usually it uploads a lot faster, but I guess because I'm live streaming at the same time in 4K 2030p maximum resolution. Okay. So now put this cable up. I'm still a little bit tired, actually. Maybe I should eat a little something, get the energy back going. Okay, stick that on. Okay. What are we thinking, guys? Should I eat a little something real quick? Right quick? just to recharge. Should I do it? Should I? Trying to think. Spilled some water like a boss. If you're not 21 and you're still not spilling water all over yourself, what are you doing? Oh, I should do laundry. I have to, actually. I need to. It's on the bottom. Okay. Fuck. I hate that I got these. I thought this would just be normal Tide Pods, but it's 25 only. And they're like huge. So it really makes my clothes smell detergenty, which I don't like. But I bought them. This is my fate. So it sucks for you guys. You're gonna have to hear laundry being done in the background. Not my problem. I could turn off the compressor on the microphone so you don't have to hear the laundry as much. I'll just speak closer to the mic. I think that should give a little bit less of an issue when it comes to audio quality. Also, I didn't fill up my Brita filter before starting the laundry. That's okay. Still got some water. So put this back. Okie dokie, guys. Okie dokie. Okay. I have like an instinctual habit of like going to tap my phone screen so I can just like look at it for stimulation. I need to stop doing that I don't know how to stop doing that. Self-control, obviously, is the first answer, but like, okay, I have it off silent, so I'll just put it behind me, actually. Put the phone behind me. I think that'll help. 6,000 steps today. That's pretty good. I can actually probably hit 10k steps today. I didn't set that as my goal, but I didn't go to the gym today. So I think on the days where I don't go to the gym, I should strive to get 10k steps. Days where I do go to the gym, 10k steps isn't super important of a goal. But guys, we're picking up where we left off with Power Series. Of course. Let's quit Discord. Who needs that open? Ever. Open up yay old whiteboard so we can write and do stuff, draw, and we are going to get straight into it, ladies and gentlemen, straight into it with Power Series. So let's recap. What did we look at last time? So we read the introduction of the Power Series, uniform convergence of sequences, uniform convergence and differentiation. Yeah, so previously we had a notion of pointwise convergence for functions, but then we had uniform convergence for functions. And with uniform convergence, then we could do a whole bunch of new stuff. Since it converges uniformly, then we can talk about Cauchy criterion. Okay, Cauchy criterion basically talks about uniform convergence. And then with uniform convergence, we can now talk about continuity. Okay, so with uniform convergence, then we can talk about differentiable limit theorem. Which basically means if a sequence fn prime converges uniformly on a compact set to a function g, then the function f is differentiable and f prime is equal to g. Okay, so this guarantees that a function is differentiable. So convergence does not always necessarily imply, continuity does not always imply differentiability. Actually, no, we're assuming that they're differentiable. So we're talking about if the derivative of the sequence converges, then the function itself is differentiable. Okay, so we're talking about sequences of functions and a function itself. I don't really get what's the point of this, actually. Oh, we don't even assume that the sequence of derivatives converges uniformly. Oh, we assume the sequence of derivatives converges uniformly, and it's strong enough to prove that Fn converges uniformly, in fact. So let Fn be a sequence of differentiable functions defined on the closed interval, and assume Fn prime converges uniformly. If there exists a point x0, then Fn converges uniformly. Okay, so this is kind of where we left off with this last thing. This last theorem, let Fn be a sequence of differentiable functions defined on the closed interval AB, and assume Fn prime converges uniformly to a function g. If there exists a point x0, which is an element of AB for which Fn x0 is convergent, then Fn converges uniformly. Moreover, the limit function f is equal to limit of Fn is differentiable and satisfies f prime is equal to g. Okay, I would have to actually look at questions to like actually understand like why does that even matter. We looked at series of functions, so we basically applied all of our previous things that we found for series, infinite series, and we applied it to an infinite series of functions as well. So our stuff kind of works, term by term continuity. Yep. Oh, okay. The reason why we wanted uniform convergence is because uniform convergence guarantees continuity. Yes. Okay, it's making sense now. Okay, then we had a series of function term by term continuity theorem. Yes. So then now we can talk about if a series of functions converges uniformly, then f is continuous. And then term by term differentiability. If a series of differentiable function of derivatives converges uniformly, then the actual series converges uniformly to a differentiable function f of x. Yes. So we can talk about if there exists a single point where it converges, then the whole thing will converge uniformly. Okay, interesting. Cauchy criterion, if this infinite series of functions converges uniformly. Yes, okay. Okay, so, okay, again, let's cover why are we even, you might be asking. Now, you might be asking yourself, why are we even reading to begin with? What's the point of this? Well, the reason why we're reading to begin with is basically to, one, refresh our memory of things that we've learned so far, and two, kind of just have a little bit of like an inkling, implant a kind of idea, a thought of if we see this problem in an actual midterm, like, oh, I'm kind of remembering what this is. Let me think about it. You know, like what was the textbook? You can kind of build up the story of what's going on in your mind, see how things depend on each other. And it'll also help for midterm prep, final prep as well, because if I see a question and I'm like, oh shit, this is dealing with uniform convergence, I kind of know what chapter it was at, and so then going back to the chapter, then I'll be more familiar with kind of being like, oh yeah, I'm refreshing my memory, rather than seeing it for the first time. It's like you see him for the first time, like a burst of ammunition I was shot out of a 9, given everything I got, so yeah, it better be my time. To say I wouldn't make it, that's the reason, that's the rhyme now. Feeling like I'm thinking about his son. No food in my stomach, hoping that tomorrow gonna come. Okay, so we don't need to read Weierstrass approximation theorem, right? Yeah, because we didn't cover that in class, just 6.6, and then 7.2. That's pretty much it. So, let's bang this out. Yeah, let's do it. So, Power series. Power series. Okay. Tilt the chair. Adjust the mic a little bit. Okay. Yeah, you guys are going to hear the washing machine. Who cares, though? Not my problem. Not my problem. I have to do laundry. Okay. 6.5 Power series. It is time to put some mathematical teeth into our understanding of functions expressed in the form of a power series. That is, functions of the form f of x is equal to... Wait, do I have clothes in the dryer? I have a couple of clothes in the dryer. Not much though, so. Okay. Back to reading. It's time to put some mathematical teeth into our understanding of functions expressed in the form of a power series. That is, functions of the form f of x is equal to the summation of some polynomial. The first order of business is to determine the points x, which are elements of the reals, for which the resulting series on the right-hand side converges. This set certainly contains x equals 0, and as the next result demonstrates, it takes a very predictable form. Theorem 6.5.1. If a power series, the infinite sum of a polynomial, converges to some point x naught, then it converges absolutely for any x satisfying the absolute value of x is less than the absolute value of x naught. Proof. If the infinite sum of x naught converges, then the sequence of terms a n x naught to the n is bounded. Yes, because a series converges if it if a power series, if a series is converging, if an infinite series is converging, then it is also bounded. In fact, it converges to 0. Yes, because if an infinite series converges, it will converge to 0 because you're adding up things. So it should converge to 0. Let m be greater than 0. Satisfy an x naught n is bounded, so it's less than or equal to m for all n, which is a natural number. If x is an element of R, satisfying that the absolute value of x is less than x naught, then an x to the n is equal to an x naught to the n times x over x naught, which is bounded by m x over x naught. Yes. But notice that the infinite sum of m times x over x naught to the n is a geometric series with ratio x over x naught less than 1. And so it converges because x is less than x naught. Okay. By the comparison test, an xn converges absolutely. Okay. Yeah, because m is just some number. It's just some constant. Any constant that's greater than 0. Any positive constant. And then x over x naught is a geometric series. Let's bust out the Notebook. Yes, the movie with Ryan Gosling. That's totally what I meant. Pretty sure I took some notes on this. Why did I skip so many pages? Yep. So this is a geometric series. And so it converges. Yeah, because the ratio, so r to the n, where r is less than 1, is a geometric series that converges. And so this is a ratio that is less than 1 because you have x, which is smaller than x naught. So by the comparison test, an xn converges absolutely. The main implication of theorem 6.5.1 is that the set of points for which a given power series converges must necessarily be 0, R, or a bounded interval centered around x equals 0. Because of the strict inequality in theorem 6.5.1, there is some ambiguity about the endpoints of the interval, and it is possible the set of convergent points may be of the form negative r to r, blah blah blah. The value of r is referred to as the radius of convergence of a power series, and it is customary to assign r the value 0 or infinity to represent the set 0, or the real numbers respectively. Some of the standard devices for computing the radius of convergence for a power series are explored in the exercises. Of more interest to us in this investigation of the properties of functions defined in this way is the investigation. Are they continuous? Are they differentiable? If so, can we differentiate the series term by term? What happens at the endpoints? Establishing uniform convergence. The positive answers to the preceding questions and the usefulness of power series in general are largely due to the fact that they converge uniformly on compact sets contained in their domain of convergent points. As we are about to see, a complete proof of this fact requires a fairly delicate argument attributed to the Norwegian mathematician Niels Henrik Abel. A significant amount of progress, however, can be made with the Weierstrass M-test. Theorem 6.5.2. If a power series, the infinite sum of that, converges absolutely at a point x naught, then it converges uniformly on the closed interval negative c to c, where c is equal to x naught. So if it converges at a point x naught, then it converges uniformly on the closed interval. This proof requires a straightforward application of the Weierstrass M-test. Did we prove it in class? Yes, we did. For all x, which is an element of negative x naught to x naught, an to the x is bounded by an x naught because x is less than or equal to x naught. And then mn, series of mn converges since you're, so you call that mn, and that series converges since you're assuming absolute convergence at x naught. Then you apply Weierstrass M-test. So in the series of an, xn converges uniformly if x is there. Okay, pretty straightforward. So you just have your power series x to the n, and then you're saying let x be an element of negative absolute value of x naught absolute value, and then what you're saying is then you can, this is bounded by this x naught to the n. This is your function. This is mn, and notice that mn converges by the assumption that an x to the n converges absolutely, yes. So if an x to the n converges and an x naught converges at a point, because you're assuming it, then it converges uniformly on the closed interval. So then with Weierstrass M-test, then you'll just have that this series converges uniformly. So we assume that it's converging, and we just want to show that it converges uniformly. Yeah, so this is pointwise absolute convergence. So we're basically showing that it converges uniformly and also absolutely uniformly. But yeah, okay. So it's one of those math proofs that it's like, okay, dude, I guess so. Sure. For many applications, Theorem 6.5.2 is good enough. For instance, because any x, which is an element of this radius of convergence, is contained in the interior of a closed interval, which is a subset of this radius of convergence, it now follows that a power series that converges on an open interval is necessarily continuous on this interval. But what happens if we know that a series converges at an endpoint of its interval of convergence? Does the good behavior of the series on negative r to r necessarily extend to the endpoint x equals r? If the convergence of the series at x equals r is absolute convergence, then we can rely on Theorem 6.5.2 to conclude that the series converges uniformly on the set negative r to r. The remaining interesting open question is what happens if a series converges conditionally at a point x equals r. We may still use Theorem 6.5.1 to conclude that we have pointwise convergence on the interval negative r to r, but more work is needed to establish uniform convergence on compact sets containing x equals r. Abel's theorem. We should remark that if the power series g of x is equal to that converges conditionally at x equals r, then it is possible for it to diverge when x equals negative r. The series sum negative 1 to the n, x to the n over n with r equals 1 as an example. To keep our attention fixed on the convergent endpoint, we will prove uniform convergence on the set 0 to r. The first step in the argument is an estimate that should be compared to Abel's test for convergence of series developed back in chapter 2. Lemma 6.5.3, Abel's lemma, let Bn satisfy B1 is greater than or equal to B2, which is greater than or equal to B3, so this is a decreasing sequence, doesn't even have to be monotone. And let the summation an be a series for which the partial sums are bounded. In other words, there exists an a greater than 0 such that a1 plus a2 plus dot 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 plus an is less than or equal to a. For all n, which is a natural number, then for all n, which is a natural number, what? Yeah, I think that's just a typo. For all n, that's a natural number. A1b1 plus A2b2 plus A3b3 plus dot 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 is less than or equal to AB1. So you have a series of numbers that is decreasing, and you have a series for which the partial sums are bounded. Then the product of the series with these are also going to be bounded. Okay. Let Sn equal A1 plus A2 plus dot 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 plus An. Using the summation by parts formula derived in exercise 2.7.12, we can write the summation of AK BK is equal to Sn Bn plus 1 plus SK BK minus BK plus 1, which is bounded by A Bn plus 1 because we're assuming that Sn, which is equal to this, is bounded by A, so A Bn plus 1 plus the summation of A, because SK is also bounded by A, BK minus BK plus 1, which is A Bn plus 1 plus A B1 minus A Bn plus 1, which is equal to A B1. Because these two cancel out. Okay. Sure. It is worth noting that if A were an upper bound on the partial sums of the summation of absolute value of An, then the proof of lemma 6.5.3 would be a simple exercise in the triangle inequality. The point of the matter is that because we are only assuming conditional convergence, the triangle inequality is not going to be of any use in proving Abel's theorem, but we are now in possession of an inequality that we can use in its place. So this is Abel's lemma, this is Abel's theorem. Let g of x equal to the summation of a power series. Let g of x equal a power series that converges at the point x equals to r, which is positive. That's not the actual be real. Okay, let g of x be a power series that converges at the point x is equal to r, which is positive. Then the series converges uniformly on the interval 0 to r. A similar result holds if the series converges at x equals negative r. Okay. To set the stage for an application of lemma 6.5.3, we first write g of x is equal to an x to the n, which is equal to an r to the n times x over r to the n. Let epsilon be greater than 0 by the Cauchy criterion for uniform convergence of series. We will be done if we can produce an n such that n is greater than m, which is greater than or equal to n, which implies that a m plus 1 r to the m plus 1 plus a m plus 2 plus a n r n is less than epsilon. Because we are assuming that this converges, yep, the Cauchy criterion for convergent series of real numbers guarantees that there exists an n such that this is less than epsilon over 2. But now, for any fixed m, we can apply Abel's lemma to the sequences obtained by omitting the first m terms. Using epsilon over 2 as a bound on the partial sums of this infinite sum, and observing that x over r is decreasing, an application of Abel's lemma to equation 1 yields that. Okay. It's kind of confusing. Kind of a lot of indices and such. But sure. Don't really get what's the point of Abel's theorem. I guess now we have a power series that converges at a point. And since it converges at a point, then we can argue that the series converges uniformly on this interval within this radius of convergence. Oh, I guess I kind of see what that means. So if we're saying that, like, okay, this series converges, which it'll converge to 0 because it's a series, right? If we're saying this series converges at some point, if we take any point that's less than that, surely it necessarily follows that if we're summing up this series and it's converging to 0, for any point less than that, intuitively, it should also just converge to 0, right? If we're taking this interval and we're saying, like, okay, it converges at this point, let's say this is R. This is where this infinite sum converges. Then, for any value that's less than that, all the way to 0, it should also converge. Also, if we say that it converges at negative R, then the argument still holds. But we haven't proved absolute convergence. So the series just converges uniformly on this interval. We're not assuming that if it converges at R, well, I guess if it converges at the absolute value of R, then this would follow, I guess. Maybe, I think. But yeah, okay. Do 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 do. Ba-bum. Yo, I shot some sick videos on this camera today that I think are going to be really freaking cool. There was one in particular. There was this video, which I'll show, hopefully. Look at how cool that looks, dude. That looks so dope. The frame rate, like the way that it's picking it up, the lens flare as well. Fuck, man. It's a good decision. It's really thin too. I can get a new kind of vibe because the Canon camera that I have, it's kind of old, kind of vintage, but it's not like the vintage look. It's not the vintage digital look. It's just more so kind of like a cool digital looking kind of camera. It's not the vintage old, like, you know, digital Sony camcorder kind of look. Okay. Damn, guys, we're almost done reading, actually. Look at that. The success of power series. An economical way to surmise the conclusions of Theorem 6.5.2 and Abel's theorem is with the following statement. If a power series converges pointwise on the set A, which is a subset of the reals, then it converges uniformly on any compact set K, which is a subset of A. Oh, wow. Okay, there we go. That's the summation of it all. A compact set contains both a maximum x1 and a minimum x0, which by hypothesis must be in A. Abel's theorem implies the series converges uniformly on the interval x0 and x1, and thus also on K. Ah, okay. Yeah, if it converges uniformly, then you can form any radius of convergence with any point in here. Oh, yeah, okay. This fact leads to the desirable conclusion that a power series is continuous at every point at which it converges. Not sure how you connect that. I guess if it converges uniformly, converging series are continuous. Is that the argument? This fact leads to the desirable conclusion that a power series is continuous at every point at which it converges. To make an argument for differentiability, we would like to appeal to Theorem 6.4.3. However, this result has a slightly more involved set of hypotheses. In order to conclude that a power series, this is differentiable, and that term-by-term differentiation is allowed, we need to know beforehand that the differentiated series that converges uniformly. Okay. If a power series converges for all x, which is within this radius of convergence, then the differentiated power series converges at each x, which is inside that radius of convergence as well. Consequently, the convergence is uniform on compact sets contained within this radius of convergence. Proof is exercise 6.5.5. Okay. Did we prove that in class? Yes, we did. So what do we say? We're saying a power series is continuous at every point that it converges. So if fn of x infinite sum converges uniformly to f of x, and if fn is continuous for all n, then f is continuous. Take any x naught, which is an element of the reals, such that an x naught n converges. So we have some k, which is a compact set within the radius of convergence. Uniform, this means that there's uniform convergence of an xn on k. Therefore, an xn is continuous at r, and thus r plus x? I don't even know what I wrote there. But okay, sure. Oh, we didn't know. This isn't even we didn't even look at the differentiation one, but okay. We should point out that it is possible for a series to converge at an endpoint x equals r, but for the differentiated series to diverge at this point. The series infinite sum x to the n over n has this property when x equals -1. On the other hand, if the differentiated series does converge at a point x equals r, then Abel's theorem applies, and the convergence of the differentiated series is uniform on compact sets that contain r. With all the pieces in place, we summarize the impressive conclusions of this section. Assume f of x is equal to a power series, converges on an interval a, which is a subset of the reals. The function f is continuous on a and differentiable on any open interval, -r to r, which is a subset of a. The derivative is given by f prime of x, which equals the the differentiated power series. Moreover, f is infinitely differentiable on -r to r, and the successive derivatives can be obtained via term-by-term differentiation of the appropriate series. Proof. The details for why f is continuous have been discussed. Theorem 6.5.6 justifies the application of the term-by-term differentiability theorem, which verifies the formula for f prime. A differentiated power series is a power series in its own right, and Theorem 6.5.6 implies that although the series may no longer converge at a particular endpoint, the radius of convergence does not change. Okay. By induction, then, power series are differentiable an infinite number of times. Great. So we prove this using rigorous logic. And now we're on to Taylor series. Our study of power series has led to some enthusiastic conclusions about the nature of functions of the form f of x is equal to a0 plus a1x plus blah blah blah. Despite their infinite character, power series can be manipulated more or less as though they are polynomials. On its interval of convergence, a power series is continuous and infinitely differentiable, and successive derivatives or antiderivatives can be computed by performing the desired operation on each individual term in the series, just as it is done for polynomials. In section 6.1, we informally encountered the powerful idea that familiar functions such as arctan of x and square root of 1 plus x can be represented as power series. This is a game-changing revelation. If a function can be represented as a power series, and a power series can be treated like a polynomial, then vast new possibilities are suddenly available for the kinds of calculations that can be undertaken. Given this state of affairs, it is natural to wonder whether all of the well-behaved, i.e. infinitely differentiable, functions of calculus might have representations as power series. In the examples and exercises in this section, we will assume the familiar properties of the trigonometric, inverse trigonometric, exponential, and logarithmic functions. Rigorously defining these functions is an important exercise in analysis. In fact, one of the most common methods for providing proper definitions is through power series, a point of view that is explored in section 8.4. The point of this discussion, however, is to come at this question from the other direction. Assuming we are in possession of an infinitely differentiable function such as sine x, can we find suitable coefficients an so that sine of x is equal to a naught plus a1x plus a2x squared plus dot 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 for at least some non-zero values of x? Manipulating series. In section 6.1, we generated several new series representations starting from the formula 1 over 1 minus x is equal to 1 plus x squared, blah blah blah, proved in example 2.7.5. At the time, we were not fully concerned with supplying rigorous proofs, but we have since done the bulk of the work necessary to confidently assert that manipulations in 6.1 are perfectly valid. Example 6.6.1. Theorem 6.5.7 applied to equation 1 gives 1 over 1 minus x squared is equal to 1 plus 2x plus 3x squared plus blah blah blah. What about the series we generated for arctan of x? The substitution of negative x squared for x in 1 doesn't cause any problem. The content of exercise 6.5.4 is that we can take the term-by-term antiderivative of the series and arrive at an antiderivative for 1 over 1 plus x squared. Noting that arctan of 0 equals 0, it follows that arctan of x is equal to x minus 1 over 3 x cubed plus blah 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 for all x which is an element of negative 1 to 1. In fact, this formula is also valid for x equals plus or minus 1. Similar methods can be used to find series representations for functions such as log 1 plus x and x over 1 plus x squared. Taylor's formula for the coefficients. Manipulating old series to produce new ones was a well-honed craft in the 17th and 18th centuries, but there also emerged a formula for producing the coefficients from scratch, a recipe for generating a power series representation using only the function in question and its derivatives. The technique is named after the mathematician Brooke Taylor, who published it in 1715, although it was certainly known previous to this date. Given an infinitely differentiable function f defined on some intervals centered at 0, the idea is to assume that f has a power series expansion and deduce what the coefficients must be. Theorem 6.6.2, Taylor's formula. Let f of x equals a naught plus a1x plus a2x squared plus blah 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 be defined on some non-trivial interval centered at 0. Then the coefficients an equals the nth derivative of f at 0 over n factorial. Exercise 6.6.3 is the proof. Proof is homework. Let's use Taylor's formula to produce the so-called Taylor series for sine x. For the constant term, we get a naught equals sine 0 equals 0, then a1 equals cosine of 0 equals 1, a2 equals negative sine 0 over 2 factorial equals 0, and a3 equals negative cosine 0 over 3 factorial equals negative 1/3 factorial. Continuing on, we are led to the series x minus x cubed over 3 factorial plus blah blah blah. So can we say that the series equals sine x? Well, we need to be very clear about what we have proved to this point. To derive Taylor's formula, we assumed that f actually had a power series representation. The conclusion is that if f can be expressed in the form f of x is equal to this power series, then it must be that the coefficients an are equal to the nth derivative of f at 0 over n factorial. But what about the converse question? Assume f is infinitely differentiable in a neighborhood of 0. If we let an equal f n at 0 over n factorial, does the resulting power series converge to f of x on some non-trivial set of points? Does it converge at all? If it does converge, we know that the limit of functions the limit function is an infinitely differentiable function whose derivatives at 0 are exactly the same as the derivatives of f. Is it possible for this limit to be different from f? In other words, might the Taylor series of a function converge to the wrong thing? Let Sn of x equal to a naught plus a1x plus a2x squared plus dot 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 plus an x to the n. The polynomial Sn of x is a partial sum of the Taylor series expansion for the function f of x. Thus, we are interested in whether or not the limit as n approaches infinity of Sn of x equals f of x for some values of x besides 0. Lagrange's remainder theorem. Okay, so basically we're going to show that the error, if the error is non-trivial, non-zero, then you cannot express it as a Taylor series. Okay. So a powerful tool for analyzing this question was provided by Joseph Louis Lagrange. The idea is to consider the difference En of x, which is equal to f of x minus Sn of x, which represents the error between f and the partial sum Sn. Let f be differentiable n plus 1 times on negative r to r. Define an equals fn at 0 over n factorial for n equals 0, 1, all the way up to capital N. And let Sn of x equal to a naught plus a1x plus blah blah blah, all the way to an x to the n. Given x not equal to 0 in this radius of convergence, there exists a point C satisfying that the absolute value of C is less than the absolute value of x, where the error function En of x is equal to f of x minus Sn of x satisfies En of x is equal to f to the n plus 1 C over n plus 1 factorial times x to the n plus 1. What does this mean? I don't really understand, like, what the hell, why, what is this? Well, let's keep reading. Before embarking on a proof, let's examine the significance of this result. Yeah, what is the significance? Proving Sn of x converges to fx is equivalent to showing En of x. Proving this is equivalent to showing En of x converges to 0. There are 3 components to the expression for En of x. In the denominator, we have n plus 1 factorial, which helps to make En small as n tends to infinity. In the numerator, we have x to the n plus 1, which potentially grows depending on the size of x. Thus, we should expect that a Taylor series is less likely to converge the farther x is chosen from the origin. Finally, we have f to the n plus 1 of c, which is a bit of a mystery. For functions with straightforward derivatives, this term can often be handled using a suitable upper bound. Example 6.6.4. Consider the Taylor series for sine of x generated earlier. How well does s5 of x equal to x blah 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 approximate sine x on the interval negative 2 to 2? Lagrange's remainder theorem asserts that the difference between these two functions is e5 of x equals sine of x minus s5 of x, which is equal to negative sine c over 6 factorial times x to the 6 for some c which is in this interval. Not knowing the value of c, we can still be quite certain that sine of c is less than or equal to 1, because x is inside of negative 2, 2, we have e5 of x is less than or equal to 2 to the 6 over 6 factorial, which is approximately equal to 0.089. To prove that Sn of x converges uniformly to sine x on negative 2 to 2, we observe that the f to the n plus 1 c term in the Lagrange formula will never exceed 1 in absolute value. Thus, En of x is equal to f to the n plus 1, blah blah blah, is bounded by 1 over n plus 1. Yeah, because you can bound sine by 1. 2 to the n plus 1, bounding x on these endpoints. Because factorials grow significantly faster than exponentials, it follows that en of x grows to 0 uniformly on negative 2 to 2. Replacing the constant 2 with an arbitrary constant r has no effect on the validity of the argument, and so the Taylor series converges uniformly to sine x on every interval of the form negative r to r. Yes, because this will still grow significantly faster, approaching 0. Okay. Show me the proof. Proof of Lagrange's remainder theorem. The Taylor coefficients are chosen so that the function f and the polynomial Sn have the same derivatives at 0, at least up through the nth derivative, after which Sn becomes a 0 function. In other words, f to the n of 0 is equal to Sn to the n of 0 for all 0, which implies the error function En of x equals f to the x, f of x minus Sn satisfies... Okay, what the fuck? Oh, yeah, okay. The key ingredient in this argument is the generalized mean value theorem from chapter 5. To simplify notation, what was the generalized mean value theorem again? What was the mean value theorem about? It was Rolle's theorem, kind of, right? Yeah, where there exists some point where the slope, the derivative, which is the slope, is equal to the endpoints. Line of the endpoints, yeah. So you have some point C, which is here, where the slope is equal. And then generalized mean value theorem. Which is f prime of C over g prime of C is equal to f of B minus f of A over GB minus G of A. That kind of looks like the fundamental theorem of calculus, not gonna lie. Okay. Apply... To simplify the notation, simplified notation, let's assume x is greater than 0, and apply the generalized mean value theorem to the functions enx and x to the n plus 1 on the interval 0x. Thus, there exists a point x1, which is inside this interval, such that enx over x to the n plus 1 is equal to en prime of x1 over the derivative of x to the n plus 1, which is that. Now apply the generalized mean value theorem to the functions e to the apply to this of at x on this interval. Together there exists a point x2 where that, and then continuing in this manner, you have this error which should be equal to this. Now set C equals to x to the n plus 1, because Sn to the n plus 1 of x equals 0, we have that this equals this, and it follows that En of x can then be written as this as desired. Okay, so as long as it's differentiable n plus 1 times on this, and then if x does not equal 0, there exists a point C where the error function can be written as this, so then thus yeah. Taylor series centered at a not equal to 0. Throughout this chapter, we focused our attention on series expansions centered at 0, but there is nothing special about 0 other than notational simplicity. If f is defined in some neighborhood of A, and infinitely differentiable at A, then the Taylor expansion around A takes the form of some constant times x minus a to the n, where Cn is equal to that. This is a n in our previous example, but now we're calling it Cn. Setting En equal to this, as usual, Lagrange's remainder theorem in this case says that there exists a value C between a and x, where that is equal to that. So we derive an alternate remainder formula due to Cauchy that requires more general expansions for its derivative. Okay. A counterexample? Do I need to look at a fucking counterexample? And now our laundry is done. So we can turn the compressor back on so we're not going to be peaking. Probably peaked a couple times. But that's okay. That's alright. Alright, so we're going to read this. And the epilogue. Actually, let's just finish reading this. Actually, I have to pee, so I'm going to read this, and then we're going to put up the close, and then read the epilogue, and 7.2, and we will be done. So, Lagrange's remainder theorem is extremely useful for determining how well the partial sums of the Taylor series approximate the original function, but it leaves unresolved the central question of whether or not the Taylor series necessarily converges to the function that generated it. The appearance of f to the n plus 1 c in the error formula makes any general statement impossible. The Cauchy form of the remainder just mentioned provides another way to represent the error between the partial sum Sn and the function f of x. And there are others still, but none lend themselves to a proof that Sn approaches f. This is because no such proof exists. Let g of x equal to e to the negative 1 over x squared for x not equal to 0, and 0 for x equals 0. Computing the Taylor coefficients of this function, it is clear that a naught equals g naught equals 0. To compute a1, we write a1 is equal to g prime naught, which equals to the limit of this, which equals to the limit of that, which equals to the limit of 1 over x, where both numerator and denominator tend to infinity as x approaches 0. Applying the infinity over infinity version of L'Hopital's rule, we see this limit approaches 0. This tells us that g is flat at the origin. But in exercise 6.6.6, evil, we outline the rest of the proof showing that Gn naught equals 0 for all n, which is an element of the naturals. In other words, g is extremely flat at the origin. The implications of this example are highly significant. The function g is infinitely differentiable, and every one of its Taylor coefficients is equal to 0. By default, then its Taylor series converges uniformly on all r to the 0 function. But other than at x equals 0, g of x is never equal to 0. The Taylor series for g of x converges, but it does not converge to g of x except at the center point x equals 0. The unmistakable conclusion is that not every infinitely differentiable function can be represented by its Taylor series. ChatGPT, can you explain this? I didn't really understand that. Okay. Also, just kidding, guys. We still need to drain out the thing. Oh, that's a lot of water. Okay. This excerpt is discussing a concept from real analysis concerning Taylor series, a powerful tool in mathematics for approximating functions that are infinitely differentiable at a point. The text begins by referencing Lagrange's remainder theorem, which is used to estimate the error when approximating a function by its Taylor series up to a certain number of terms. It highlights a limitation of the theorem. It doesn't answer whether the Taylor series of a function actually converges to the function itself over the whole domain. The main focus here is on the function gx defined piecewise. This function is smooth and infinitely differentiable everywhere on the real number line, including at x equals 0, but it has a peculiar property. All of its Taylor coefficients at x equals 0 are 0. This means that the Taylor series for this function, when expanded at x equals 0, is identically 0 for all terms, which is obviously not equal to g of x except at x equals 0. What the fuck? All of its Taylor coefficients at x equals 0 are 0. This means that the Taylor series for this function, when expanded at x equals 0, is identically 0 for all terms, which is obviously not equal to g of x, except at x equals 0. The text then shows how to compute the first derivative of gx. To demonstrate this, they use L'Hopital's rule. In applying L'Hopital's rule, they find that the limit of g prime of x as x approaches 0 is also 0. The implications of this example is profound. It tells us that there exist smooth, infinitely differentiable functions whose Taylor series do not converge to the function outside of the center of expansion. This means that the infinite differentiability does not guarantee that a function is equal to its Taylor series. Challenging the common intuition that Taylor series always provide a great representation of such functions. Okay. Just realized I wasn't shouting out the songs that you're listening to. And I had it turned down quite a bit. Okay. Epilogue. The argument sketched out here for the Weierstrass approximation theorem is due to Henri Lebesgue, who published his proof in 1898. Its greatest virtue is its relative simplicity. Starting from a single special case, the absolute value function, we manage to bootstrap our way up to an arbitrary continuous function. A downside of this approach is that by the time you reach the case of a general continuous function, there's no practical way to explicitly write down a formula for the polynomial that approximates it. There are a number of other proofs for Weierstrass approximation theorem that don't have this drawback. A particularly popular one was provided by Sergei Bernstein. Bernstein employs a family of polynomials now called Bernstein polynomials that have become important in their own right. Weierstrass's original approach was also quite elegant. His proof was much in common with the proof of Fayer's theorem in section 8.5 on Fourier series. Not coincidentally, it is possible to derive yet another proof of Watt as a corollary to Fayer's theorem. The Weierstrass approximation theorem is set on a closed interval AB. Exercise 6.7.9 is included to emphasize the importance of the closed and bounded nature of the domain, but it should not be too surprising that the theorem will remain true if we replace AB with an arbitrary compact set. What about replacing the set of polynomials? Are there other collection of relatively simple continuous functions that can be used to approximate an arbitrary continuous function? Sure there are. In theorem 6.7.3, we saw that the polygonal functions have this property. I'm gonna take out the headphones. Makes it weird to read while having them on. In theorem 6.7.3, we saw that polygonal functions have this property, and there are other examples as well. In the late 1930s, Marshall Stone proved a far-reaching conclusion of the Weierstrass approximation theorem. Stone's version of Weierstrass approximation theorem starts with an arbitrary complex set K and a collection C of continuous functions on K with the following three properties. Did we cover Weierstrass approximation theorem? No, we did not. We just went straight to the Riemann integral. And then, yeah. Okay, let's read this one about Taylor series. The story from section 6.6 surrounding Taylor series expansion also deserves a final word. The ingenuity with which Euler and others found and exploited power series representations for the cast of familiar functions from calculus understandably led to speculation that every function could be represented in such a fashion. The term function at this time implicitly referred to functions that were infinitely differentiable. The point of view effectively ended with Cauchy's discovery in 1821 of the counterexample presented at the end of section 6.6. So under what conditions does the Taylor series necessarily converge for the generating function? Lagrange's remainder theorem states that the difference between the Taylor polynomial Snx and the function f of x is given by that the n plus 1 factorial term in the denominator grows more rapidly than the x to the n plus 1 term in the numerator. Thus, if we knew, for instance, that f to the n plus 1 the n plus 1 derivative of f at c is bounded by m for all c and n, we could be sure that en of x approaches 0, and hence that Sn of x converges to f of x. This is the case for sine, cosine of x, and e to the x, whose derivatives do not grow at all as n approaches infinity. It is also possible to formulate weaker conditions on the rate of growth of f to the n plus 1, the n plus 1 derivative of f, that guarantee convergence. It is not altogether clear whether Cauchy's counterexample should come as a surprise. The fact that every previous search for a Taylor series ended in success certainly gives the impression that a power series representation is an intrinsic property of infinitely differentiable functions. But notice what we are saying here. A Taylor series for a function f is constructed from the values of f and its derivatives at the origin. If the Taylor series converges to f on some interval, then the behavior of f near 0 completely determines its behavior at every point in negative r to r. One implication of this would be that if two functions with Taylor series agree on some small neighborhood, negative epsilon to epsilon, then these two functions would have to be the same everywhere. When it is put this way, we probably should not expect the Taylor series to always converge back to the function from which it was derived. As we have seen, this is not the case for real-valued functions. What is fascinating, however, is that results of this nature do hold for functions of a complex variable. The definition of the derivative looks symbolically the same when the real numbers are replaced with complex numbers, but the implications are profoundly different. In this setting, a function that is differentiable at every point in some open disk must necessarily be infinitely differentiable on this set. This supplies the ingredients to construct the Taylor series that in every instance converges uniformly on complex sets to the function that generated it. Oh, okay. Okay, so we should read 7.1 and 7.2, which is not super long. Before that, let's put the clothes in the dryer, I guess. Oh boy. shit leaked actually. The fuck? Rick and Morty. Rick and Morty. Rick and Morty. Rick and Morty. Rick. Okay, guys, I'm starting to get pretty tired. Holy shit. I need to finish this math homework, though. Oh, I just stack exchange it. Because I gotta fucking turn it in. God damn. Okay. All right, guys. Come on, let's do this. Let me fill up a Brita filter. It's a pound of rice. I need to get that, I need to get a bucket so I can do the rice bucket thing for my hands. Yeah, okay. Holy shit, I'm really petering out. I'm getting tired. Oh my god. All right. How should integration be defined? The fundamental theorem of calculus is a statement about the... Why did I hear my phone? What the fuck am I hearing? I'm hearing things now. The fundamental theorem of calculus is a statement about the inverse relationship between differentiation and integration. It comes in two parts, depending on whether we are differentiating an integral or integrating a derivative. Under suitable hypotheses on the functions f and f, the fundamental theorem of calculus states that the integral from a to b of f prime of x dx is equal to f of b minus f of a, and if g of x is equal to the integral from a to x of f of t dt, then g prime is equal to f of x. Before we can undertake any type of rigorous investigation of these statements, we need to settle on a definition for the integral from a to b of f. Historically, the concept of integration was defined as the inverse process of differentiation. In other words, the integral of a function f was understood to be a function f that satisfied f prime is equal to f. Newton, Leibniz, Fermat, and other founders of calculus that went on to explore the relationship between antiderivatives and the problem of computing areas. This approach is ultimately unsatisfying from the point of view of analysis because it results in a very limited number of functions that can be integrated. Recall that every derivative satisfies the intermediate value property, Darbo's theorem. Every derivative satisfies the intermediate value property, yes, because you can find a derivative which is continuous. Because it's differentiable, then it's continuous on an interval, and because it's continuous, then it has the intermediate value property. This means that any function with a jump discontinuity cannot be a derivative. If we want to define integration via antidifferentiation, then we must accept the consequence that a function as simple as h of x is equal to 1 and 2 is not integrable on the interval 0, 2. A very interesting shift in emphasis occurred around 1850 in the work of Cauchy, and soon after in the work of Bernard Riemann. The idea was to completely divorce integration from the derivative and instead use the notion of area under the curve as a starting point for building a rigorous definition of the integral. The reasons for this were complicated. As we've mentioned earlier, the concept of a function was undergoing a transformation. The traditional understanding of a function as a holistic formula such as f of x equals x squared was being replaced with a more liberal interpretation, which included such bizarre constructions as Dirichlet's functions discussed in section 4.1. Serving as a catalyst to this evolution was the budding theory of Fourier series, discussed in section 8.5, which required, among other things, the need to be able to integrate these more unruly objects. The Riemann integral, as it is called today, is the one usually discussed in introductory calculus. Starting with the function f on AB, we partition the domain into small sub-intervals. On each sub-interval xk minus 1, xk, we pick some point ck, which is an element of these intervals, and use the y value f of ck as an approximation for f on that. Graphically speaking, the result is a row of thin rectangles constructed to approximate the area between f and the x-axis. The area of each rectangle is fck, and so the total area of all the rectangles is given by the Riemann sum, the summation of fck times that. Notice that area here comes from the understanding that areas below the x-axis are assigned a negative value. What should be evident from the graph is that the accuracy of the Riemann sum approximation seems to improve as the rectangles get thinner. In some sense, we take the limit of these approximating Riemann sums as the width of the individual subintervals of the partition tends to 0. This limit, if it exists, is the Riemann definition of integral from a to b of f. This brings us to a handful of questions. Creating a rigorous meaning for the limit just referred to is not too difficult. What will be of most interest to us, and was also to Riemann, is deciding what types of functions can be integrated using this procedure. Specifically, what conditions on f guarantee that this limit exists? The theory of the Riemann integral turns on the observation that smaller subintervals subintervals produce better approximations to the function f. On each subinterval, the function f is approximated by its value at some point ck. The quality of the approximation is directly related to the difference of f of x minus f of ck as x ranges over the subinterval. Because the subintervals can be chosen to have arbitrarily small width, this means that we want f of x to be close to f of ck whenever x is close to ck. But this sounds like a discussion of continuity. We will soon see that the continuity of f is intimately related to the existence of the Riemann integral of a to b of f. Is continuity sufficient to prove that Riemann sums converge to a well-defined limit? Is it necessary, or can the Riemann integral handle a discontinuous function such as hx mentioned earlier? Relying on the intuitive notion of area, it would seem that the integral from 0 to 2 h equals 3. But does the Riemann integral reach this conclusion? If so, how discontinuous can a function be before it fails to be integrable? Can the Riemann integral make sense of something as pathological as Dirichlet's function on the interval 0, 1? A function such as g of x equals to x squared sine of 1 over x and 0 raises another interesting question. Here is an example of a differentiable function studied in section 5.1 where the derivative g prime of x is not continuous. As we explore the class of integrable functions, some attempt must be made to reunite the integral with the derivative. Having defined integration independently of differentiation, we would like to come back and investigate the conditions under which equations 1 and 2 from the fundamental theorem of calculus stated earlier hold. If we are making a wish list for the types of functions that we want to be integrable, then in light of equation 1, it seems desirable to expect this set to at least contain the set of derivatives. The fact that derivatives are not always continuous is further motivation not to content ourselves with an integral that cannot handle some discontinuities. This guy who wrote this book is such a fucking G, man. This book is so well written. Like, it's like he didn't skip out an English class. It's like if I put this guy in an English class, he'd get an A, and if I put this guy in a math class, he'd get an A. Other than other textbooks that I read, where it's like, if I put this guy in like a physics class, he'd get an A, but if I put him in an English class, he'd get a C, and he would say that English is stupid, and there's no need to concern myself with English because physics is actually much more fundamental. Like, this guy is fucking based. Thank you, Stephen Abbott. Shout out Stephen Abbott. I will probably buy this book afterwards, honest to God. And I'll probably read the rest of this, man, because this book is fucking amazing. It's such a good book. Textbook. The definition of the Riemann integral. Although it has the benefit of some polish due to Darboux, the development of the integral presented in this chapter is closely related to the procedure just discussed. In place of Riemann sums, we will construct upper sums and lower sums, and in place of a limit, we will use a supremum and an infimum. Throughout this section, it is assumed that we are working with a bounded function f on a closed interval ab, meaning that there exists an m greater than 0 such that f of x is less than or equal to m for all x, which is an element of a and b. Partitions, upper sums, and lower sums. Definition 7.2.1. A partition P of AB is a finite set of points from AB that includes both A and B. The notational convention is to always list the points of a partition P in increasing order, and thus A is equal to x0, less than x1, less than x2, less than blah blah blah, less than xn, which equals B. For each subinterval of P, let mk equal the infimum and capital MK equal the supremum of f of x, respectively. The lower sum of f with respect to P is given by LFP is equal to this infinite sum, not infinite sum, this finite sum over k to m. Likewise, we define the upper sum with respect to P as being the sum of all of these supremums. For our particular partition P, I wrote some of this down, right? Yes. Okay. Wrote this down in the notebook. Dude, my fucking note taking is so bad, man. My God. For our particular partition P, it is clear that UFP is greater than or equal to LFP. The fact that the same inequality holds if the upper and lower sums are computed with respect to different partitions is the content of the next two lemmas. Let me see. What is... Oh, okay, yeah, you have a lower and an upper. Yeah. Okay. Of all these partitions. Yes. Yes. So the lower. So if we're talking about this, we have some function like this. We divide it into partitions, right? And then the lower is going to be whatever the lower part here is, and the upper is going to be whatever the max here is of the partition. This partition is defined by this. Yes. Okay. This is L, this is U, and then we take the sum of all these partitions. Boom, boom, boom. So a partition Q is a refinement of a partition P if Q contains all the points of P, that is, if P is a subset of Q. Okay, yeah, Q contains all the points of P, but P does not contain all the points of Q. If P contains if P is a subset of Q, then L of FP is less than or equal to L of FQ. And U of FP is greater than or equal to U of FQ. Yeah, so our lower sum is undershooting and our upper sum is overshooting. So Q is a refinement, so necessarily these lower and upper sums will have to be greater because it's more of a refinement. They're undershooting and overshooting less. Proof. Consider what happens when we refine P by adding a single point Z. Yeah, okay. Oh, this isn't the end of the proof. I thought it was just this, and I was like, okay, sure. Just consider it and it's proven. Yeah, this is exactly MK and then MK. Focusing on the lower sum for a moment, we have mk xk minus xk minus 1, mk xk minus z plus mkz minus xk minus 1 is less than or equal to m prime k plus m double prime, where m prime k is equal to the infimum from this and m double prime k is equal to the infimum from that, are each necessarily as large or larger than mk. By induction, we have L of fp is less than or equal to L of fq, and an analogous argument holds for the upper sums, except everything is just kind of flipped. Lemma 7.2.4. If P1 and P2 are any two partitions of AB, then LFP1 is less than or equal to UFP2. Proof. Let Q equal P1 union P2 and be the so-called common refinement of P1 and P2. Because P1 is a subset of Q and P2 is a subset of Q, it follows that L blah 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 is less than that, which is less than the upper, less than that. Yes. Proof. Okay. Integrability. Intuitively, it helps to visualize a particular upper sum as an overestimate for the value of the integral and the lower sum as an underestimate. As the partitions get more refined, the upper sums get potentially smaller, while the lower sums get potentially larger. A function is integrable if the upper and lower sums meet at some common value in the middle. Rather than taking a limit of these sums, we will instead make use of the axiom of completeness and consider the infimum of the upper sums and the supremum of the lower sums. Let P be the collection of all possible partitions of the interval AB. The upper integral of f is defined to be UF is equal to the infimum from UFP, where P is a element of P. In a similar way to find the lower integral of that, the following fact is not surprising. Lemma. For any bounded function f on AB, it is always the case that the upper integral is going to be greater than or equal to the lower integral. Not surprising. Definition 7.2.7 Riemann integrability. A bounded function f defined on the interval AB is Riemann integrable if UF equals LF. In this case, we define integral from AB of f or integral of AB of f of x dx to be this common value, namely integral from a to b of f is equal to UF equals LF. The modifier Riemann in front of integrable accurately suggests that there are other ways to define the integral. In fact, our work in this chapter will expose the need for a different approach, one of which is discussed in section 8.1. In this chapter, the Riemann integral is the only method under consideration, so it will usually be convenient to drop the modifier Riemann and simply refer to a function as being integrable. Criterion for integrability. To summarize the situation thus far, it is always the case for a bounded function f on AB that the supremum of the lower sums is equal to the lower sum, which is less than or equal to the upper sum, which is equal to the infimum of the upper sums. The function f is integrable if the inequality is an equality. The major thrust of our investigation of the integral is to describe as best we can the class of integrable functions. The preceding inequality reveals that integrability is really equivalent to the case of partitions whose upper and lower sums are arbitrarily close together. Did we cover that? Yes, we did. A bounded function f is integrable on AB if and only if for every epsilon greater than 0 there exists a partition p epsilon of AB such that the upper sum minus the lower sum is less than epsilon. Proof. Let epsilon be greater than 0. If such a partition exists, then the upper minus the lower is going to be less than or equal to the upper, which is less than epsilon. Because epsilon is arbitrary, it must be that the upper f equals LF, so f is integrable. The proof of the converse statement is a familiar triangle inequality. This is an if and only if. Proof of the converse statement is a familiar triangle inequality argument with parentheses in place of absolute value bars because in each case we know which quantity is larger. Because UF is the greatest lower bound of the upper sums, we know that given some epsilon greater than 0, there must exist a partition P1 such that UF_P1 is less than UF plus epsilon over 2. Likewise, there exists a partition P2 satisfying that LF_P2 is greater than LF minus epsilon over 2. Now let P of epsilon equal to the union of P1 and P2 be the common refinement. Keeping in mind that the integrability of F means UF equals LF, we can write UF_P epsilon minus LF_P epsilon is less than or equal to UF_P1 minus LF_P2, which is less than UF plus epsilon over 2 minus LF minus epsilon over 2, which is equal to, because these two are assumed to be the same, epsilon over 2 plus epsilon over 2, which equals epsilon. In the discussion at the beginning of this chapter, it became clear that integrability is closely tied to the concept of continuity. To make this observation more precise, let P equal to this be an arbitrary partition of AB, and define delta xk equal to xk minus 1. Then UFP minus LFP is equal to the sum of that. Where mk and mk are the supremum and infimum of the function on the interval respectively. Our ability to control the size of u minus L hinges on the differences mk minus mk, which we can interpret as the variation in the range of the function over the interval xk minus 1 xk. Restricting the variation of f over arbitrarily small intervals in AB is precisely what it means to say that f is uniformly continuous on this set. I should have been a math major, dude. No, this textbook is just what's making me think that. Theorem 7.2.9. If f is continuous on AB, then it is integrable. Proof. Because f is continuous on a compact set, it must be bounded. It is also uniformly continuous for the same reason. This means that given an epsilon greater than 0, there exists delta greater than 0, so that x minus y less than delta guarantees that f of x minus f of y is less than epsilon over b minus a. Now let P be a partition of AB where delta x is less than delta. Given our particular subinterval of P, we know the extreme value theorem that the supreme MK. Okay, sure. We didn't cover that in class, but yeah, okay. If f is continuous, then it must be integral. It's pretty intuitive as well, because we learned that. Okay, guys, boom. Holy, can you believe it? We are done with reading that. To-do list. Take that shit off. Okay, what I'm gonna do, 10-minute power nap because my eyes are burning. I'm gonna wake up, I'm gonna bang out the homework, and I'm gonna go to sleep. And we're gonna start tomorrow afresh, anew, brand freaking new. All right, that's it for today, guys. We are done. Good job. We read, we bled. It's only been 3 hours, technically 2.5 hours, which isn't too long, but it feels like it was much longer. But anyway, all right. Peace out, guys. See you tomorrow for another episode, another day of premium life living. Fuck this. ChatGPT sucks. I'm gonna stop paying for the premium because, oh my god, does it suck. Peace.